All right, welcome back. We continue our investigation of multiple regression. Now, it's often helpful, and sometimes even necessary, to linearly transform one or more of the variables in a regression model. In this lecture video, we investigate the impact these transformations have on the estimators of the parameters in the model, as well as on the variability of those estimators. In doing this, we develop the theory behind the results that are presented. We then focus on an important application of the general theory, that of obtaining standardized parameter estimates. Standardized parameter estimates are used by researchers to compare the relative impact of each variable on the response. But what are standardized parameter estimates, and how can they be calculated? Can they be calculated for fitted regression models when we don't have the actual data? If so, what information is needed? This would be helpful, for example, when attempting to evaluate and assess the impact of variables in regression models that have been published in journals when the raw data have not been provided. To illustrate the theory presented in the lecture, we'll use SAS Analytics Pro. We'll use ProcIML, the interactive matrix language, to implement the formulas presented in the lecture. We'll then demonstrate how to obtain standardized parameter estimates two different ways using ProcReg. So let's get started. In this lecture video, we look at the impact on parameter estimates of linear transformations of the regression variables. So let's look at an introduction. It's often useful to perform linear transformations of one or more of the variables in a multiple regression model, whether one or more of the explanatory variables, the response variable itself, or a combination of both types of variables. This can occur when one or more variables in the model need to be expressed in different units, and it can also be used to reduce the computational errors that can occur in calculating the parameter estimates when the data in different variables differ greatly in magnitude. Now, two important questions to consider are the following. How do such changes in the data impact the parameter estimates? And how can parameter estimates of model parameters based on transformed data be calculated? Do we need the raw data itself? Or can those parameter estimates be computed from the parameter estimates based on the original data, along with knowledge of the linear transformations that are to be performed on the variables? When the raw data and regression software are available, it's straightforward to construct the new variables by applying the required linear transformations to the data and then refitting the regression model using the transformed data. But if either the raw data or regression software is not readily available, one cannot refit the model, nor can the original data even be transformed. So how can we determine what the parameter estimates would be with the transformed variables? The good news is that neither the original data nor regression software are needed in order to determine what the parameter estimates would be using the new transformed variables. As long as one has the parameter estimates based on the original data, it's straightforward to calculate the parameter estimates for the new model based on the new transformed variables. We will investigate how to do this, first for the case of simple linear regression, and then for multiple linear regression. To keep the mathematical discussion manageable, for the multiple regression case, we will restrict our attention to a multiple regression model with two explanatory variables. So let's look at the impact on parameter estimates of linearly transforming variables in the case of simple linear regression. So consider the simple linear regression model, y sub I equal to beta 0 plus beta 1 times x sub I plus epsilon sub I going from 1 to n, where the epsilon sub i's are IID, or independent and identically distributed normal random variates with a mean of 0 and a variance of sigma squared. The first step, and one of the most important goals of regression analysis, is to estimate the model parameters beta 0, beta 1, and sigma squared. least squares estimation will be used to estimate beta 0 and beta 1, and the resulting parameter estimators will be denoted by beta 0 hat, beta 1 hat, and then sigma squared hat. Now recall the following summary statistics that are used in calculating the estimates of the parameters beta 0 and beta 1. The first is the mean of the response variable, y bar. That's just the sample mean of the y values. We also have the mean of the explanatory variable. And so x is the explanatory variable, and so we'll denote the mean of that variable by x bar. We use the corrected sum of products of the x's and the y's, denoted by s sub xy. The formula, the definition formula is shown here. And then we also use the corrected sum of squares of the x's. So s sub xx, which again is shown here. So these are used in calculating the least squares estimates of beta 0 and beta 1. Now consider the following linear transformations of the response variable y and the explanatory variable x. And so y sub I star, which we'll use to denote the transformed response, is equal to a sub y times the original response y sub I plus b sub y. So this is a linear transformation of the original response y sub I, and we'll again denote this by a star, so y sub I star. The transformed explanatory variable, x sub I star, is equal to a sub x times x sub I plus b sub x. Again, this is a linear transformation, in this case of the original explanatory variable. Now, using these new variables, the simple linear regression model can be written in the following form: y sub I star equal to beta 0 star plus beta 1 star times x sub I star plus epsilon sub I star. So we've got stars on everything here to indicate that these are the variables and the parameters for this new model, the new model that utilizes the linearly transformed variables. All right, and notice also that the error term here, epsilon sub I star, these are IID, again, normally distributed with a mean of 0 and a variance, which we'll denote by sigma star squared. Now, denote the least squares estimators of the parameters in this model, in particular the beta parameters, by beta 0 star hat and beta 1 star hat, and the corresponding or resulting estimate of the error variance, sigma star squared, sigma star hat squared. And so here are the questions that we're considering at this point in the lecture video. So how are the parameter estimators, beta 0 star hat and beta 1 star hat, as well as sigma star hat squared for the new model, related to the parameter estimators beta 0 hat, beta 1 hat, and sigma hat squared of the original model? So again, we had the original model, and beta 0 hat and beta 1 hat were the least squares estimators of beta 0 and beta 1 in that model, and sigma hat squared was the estimate of the error variance in that model. On the other hand, beta 0 star hat and beta 1 star hat denote the least squares estimators of beta 0 star and beta 1 star in the new model that we just saw on the previous slide. So the question is, how are those parameter estimators related to the parameter estimators from the original model? Now, the second question, and it's a very important question, is how are the variances of and the covariance between the parameters beta 0 star hat and beta 1 star hat related to the variances of and the covariance between beta 0 hat and beta 1 hat? And so we're investigating these types of relationships so that we can see whether it will be able to be possible to calculate the least squares estimators for the new model using the least squares estimators from the original model. And so let's introduce a lemma here. And I'm going to call this lemma 3.9.1. This information is more general than the information that is provided in the textbook in section 3.9. But we're going to look at a special case of this theory that actually is presented in 3.9. And so that's why I've got the 3.9 there. And then what I'm going to do, we're going to have some lemmas, theorems, and corollaries. And I'm just going to number those sequentially. So this is the first lemma, theorem, or corollary. And so it gets the number 1. So lemma 3.9.1 says the following. Let x1 through xn be n observed values of a given variable x, and define a new variable x star by the linear transformation x sub I star equal to a sub x times x sub I, the original variable, plus b sub x. Now, let x bar be the mean of the original x values. Then the arithmetic mean of the x sub I stars is related to the mean of the x sub i's by this formula. And because of the linearity of averaging, the mean of the linearly transformed variable is just that same linear transformation applied to the mean of the original variable. So a sub x times x bar plus b sub x. So that's a very simple, a very trivial result, but it is useful. And this gives us, putting it in the context of the framework of a lemma, gives us something to refer to. All right, now let's look at lemma 3.9.2. And so let x1, y1, x2, y2, and so forth up to xn, yn be n observed values of a sample of ordered pairs of variables x and y. Now define a new ordered pair of variables, x star, y star, according to the pair of linear transformations where x sub I star is equal to a sub x times x sub I plus b sub x, and y sub I star is equal to a sub y times y sub I plus b sub y. So all we're doing is just linearly transforming the x's and the y's. The corrected sum of products of the x stars and the y stars, which we will denote by s sub x star, y star, is related to the corrected sum of products of the x's and the y's, which again was denoted by s sub xy, by the following formula. So the corrected sum of products of the x's and y's, s sub x star, y star, is equal to a sub x times a sub y times the corrected sum of products of the x's and the y's. So that's, again, another fairly straightforward and simple result, but it's going to be useful in what we do coming up. Next, we have lemma 3.9.3. And so let x1 through xn be n observed values of a given variable x, and define a new variable x star by the linear transformation x sub I star equal to a sub x times x sub I plus b sub x, I going from 1 to n. Then the corrected sum of squares of the x stars, which is denoted s sub x star, is related to the corrected sum of squares of the x's, which again was denoted by s sub xx, by the following formula. So the corrected sum of squares of the x stars is equal to a sub x squared. And again, a is this value that we're multiplying against x in that linear transformation. And so this is equal to a sub x squared times the corrected sum of squares of the original variable x. All right, now we've laid the groundwork to present this theorem, theorem 3.9.4. Let x1, y1, x2, y2, and so forth up to x sub n, y sub n be a bivariate random sample. Consider the simple linear regression model for these data. Y sub I equal to beta sub 0 plus beta 1 x sub I plus epsilon sub I going from 1 to n. define a new bivariate sample denoted by x1 star, y1 star, x2 star, y2 star, and so forth, up to xn star, yn star, from the original sample according to the pair of linear transformations shown here, where x sub I star is equal to a sub x times x sub I plus b sub x, and y sub I star is the linearly transformed version of y given by a sub y times y sub I plus b sub y. And then once we've done that, let's denote this simple linear regression model associated with the new data as follows. So y sub I star plus beta 0 star plus beta 1 star times x sub I star plus epsilon sub I star. And then the least squares estimators, beta 0 star hat and beta 1 star hat, of the parameters in the new model, which is based on the linearly transformed data, are related to the least squares estimators beta 0 hat and beta 1 hat of the parameters in the model based on the original data, according to the following formulas. So beta 1 star hat is equal to a sub y over a sub x times beta 1 hat, and beta 0 star hat is equal to a sub y times beta 0 hat plus b sub y minus a sub y over a sub x times beta 1 hat times b sub x. And so if we have the least squares estimators for the original model, then it's very easy to obtain the least squares estimators for the new model, which is based on the linearly transformed variables, without having to actually transform the data and refit the model. All we have to do is calculate those least squares estimates according to or using these formulas. Furthermore, the variances of the estimators, beta 0 star hat and beta 1 star hat, and the covariance between them are given by the following formulas, which are in terms of the variances of beta 0 hat and beta 1 hat, as well as their covariance. And so we see here that the estimated variance, I've got a hat there on the bar, so this is the estimated variance of beta 0 star hat is equal to the square of a sub y times the estimated times the quantity. And so you can see here that we're multiplying that a sub y squared against this entire expression inside the parentheses. And this is given the expression here in the parentheses, the estimated variance of beta 0 hat. So that would be the estimated variance of beta 0 hat, which is obtained by fitting the original model, minus 2 times b sub x over a sub x times the estimated covariance of beta 0 hat and beta 1 hat, plus b sub x squared divided by a sub x squared times the estimated variance of beta 1 hat. The estimated variance of beta 1 hat star is equal to the square of a sub y divided by the square of a sub x times the estimated variance of beta 1 hat. And then the estimated covariance between beta 0 star hat and beta 1 star hat is given by the following expression. So again, a sub y squared times the quantity in parentheses here, 1 over a sub x, times the estimated covariance of beta 0 hat and beta 1 hat, minus b sub x divided by a sub x squared times the estimated variance of beta 1 hat. And so we see here that the variances and the covariance of beta 0 star and beta 0 star hat and beta 1 star hat can be expressed in terms of the variances of beta 0 hat and beta 1 hat from the original model, as well as their covariance. And so again, we can calculate these variances and this covariance without actually having to transform the data and refit the model. Now, proofs of results 1 and 2 are going to be provided below. Proofs of results 3 through 5 on this slide are left as an exercise. And so based on our previous work, we know that the least squares estimator of beta 1 star must be given by the following. So beta 1 star hat is equal to, by the theory of least squares, the corrected sum of squares of the x star and y star values, so s sub x star y star, divided by the corrected sum of squares of the x stars, so s sub x star x star. Now, by lemma 3.9.2, which we presented above, the corrected sum of products of the x stars and y stars is equal to a sub x times a sub y times the corrected sum of products of the x's and the y's. And by lemma 3.9.3, the corrected sum of squares of the x star values is equal to a sub x squared times the corrected sum of squares of the original x's. And so it follows that the least squares estimator of beta 1 star, which is denoted beta 1 star hat, that is equal to, we see here, s sub x star y star divided by s sub x star x star. All right, and so we have that being equal to a sub x times a sub y times s sub xy divided by a sub x squared times s sub xx. And we see here that one of the a sub x upstairs in the numerator cancels out with one of the a sub x's downstairs. And so this is equal to a sub y over a sub x times beta 1 hat. And so that proves that first result. Now, also based on what we know about least squares estimation in the context of simple linear regression, the least squares estimator of beta 0 star must be given by beta 0 star hat minus y bar star minus beta 1 star hat times x bar star. By lemma 3.1 and the result above, along with the fact that beta 0 hat is equal to y bar minus beta 1 hat times x bar, it follows that the least squares estimator of beta 0 star is given by the following. So beta 0 star hat is equal to y bar star minus beta 1 star hat times x bar star. All right, so we know that is true based on the theory of least squares estimation in the context of simple linear regression. If we plug in the expression for y bar star, we get a sub y times y bar plus b sub y minus, and then we plug in the value for beta 1 star hat that we just found. And so we get a sub y over a sub x times beta 1 hat times, and then x bar star is a sub x times x bar plus b sub x. And that simplifies to a sub y times beta 0 star, beta 0 hat, plus b sub y minus a sub y over a sub x times beta 1 hat times b sub x. So that proves that second result. Now let's look at the impact on parameter estimates if we standardize the variables. All right, and so that is what we're talking about when we talk about standardized regression parameters. And so again, we're looking at this in the context of simple linear regression. Now, a common transformation used in statistics in general, and in regression in particular, is the standardization of random variables. For example, consider the random variable x with mean mu sub x and standard deviation sigma. The standardized version of this random variable, denoted by z, is equal to x minus its mean mu sub x, and that difference divided by its standard deviation, sigma sub x. So when we do that, the new random variable z has a mean of 0 and a standard deviation of 1. Note that the standardization can be written in the following form: z equal to a sub x plus b, where a is equal to 1 over sigma sub x, and b is equal to negative mu sub x over sigma x. And so what this shows then is that standardization is a linear transformation. Now, for sample data, where the population mean and standard deviation are unknown, variables are typically standardized with respect to their sample mean and sample standard deviation. The sample mean and the sample standard deviation of the standardized data are 0 and 1, respectively. Now, with this in mind, let x1, y1, x2, y2, and so forth up to x sub n, y sub n be a random sample of bivariate data points. Consider the simple linear regression model for these data. Y sub I equal to beta 0 plus beta 1 x sub I plus epsilon sub I, where I goes from 1 to n. Define a new bivariate sample, which we'll denote by x1 star, x, or y1 star, x2 star, y2 star, and so forth up to x sub n star, y sub n star. Derive this from the original sample by standardizing each of the two variables. So x sub I star is equal to x sub I minus the mean of the x's, and then we divide that difference by the standard deviation of the x's. Likewise, y sub I star is equal to the original variable y sub I minus the mean of the y values, and then we divide that difference by the standard deviation of the y's. Then let's express the simple linear regression model associated with the new data as follows. So y sub I star equal to beta 0 star plus beta 1 star times x sub I star plus epsilon sub I star. Now, two important questions to consider are the following. How does standardizing the data impact the regression parameter estimates? What are the relationships between the parameter estimates for the model based on the standardized variables and the parameter estimates for the model based on the original data? And then finally, how are the estimated variances and covariance of the parameter estimates for the model based on standardized variables related to the estimated variances and covariance of the parameter estimates for the model based on the original data? And so we can apply the previous theorem and come up with this corollary. So this will be corollary 3.9.5. And so again, we have the same setup here. We've got our original bivariate sample along with a simple linear regression model. We derive a new sample by standardizing the x's and the y's, and then we express the simple linear regression model for the new data, as we have here at the bottom of the slide. Okay, and so when we do that, the least squares estimators, beta 0 star hat and beta 1 star hat of the parameters in the model based on the standardized data are related to the least squares estimators beta 0 hat and beta 1 hat of the parameters in the model based on the original data according to the following formulas. And so beta 1 star hat is equal to the ratio of the standard deviation of the x's to the standard deviation of the y's times beta 1 hat, and beta 0 star hat is going to be equal to 0. And what this implies then is that for the standardized data, the fitted line is going to go through the origin. Continuing on here with corollary 3.9.5, the estimated variances of the estimators beta 0 star hat and beta 1 star hat and the estimated covariance between them are given by the following formulas. So the estimated variance of beta 0 star hat is equal to 1 over the variance, 1 over the sample variance of the y values times the entire quantity here in parentheses, so the estimated variance of beta 0 hat plus 2 times x bar times the estimated covariance of beta 0 hat and beta 1 hat plus the square of x bar times the estimated variance of beta 1 hat. The variance, or the estimated variance of beta 1 star hat, is equal to the ratio of the sample variance of the x's to the sample variance of the y's times the estimated variance of beta 1 hat. And then finally, the estimated covariance of beta 0 star hat and beta 1 star hat is equal to the sample standard deviation of the x's divided by the sample variance of the y's times the estimated covariance of beta 0 hat and beta 1 hat plus x bar times the estimated variance of beta 1 hat. So that is how the least squares estimators of the parameters in the model are related to the least squares estimators in the original model. And this also shows how the variances and the covariance of the least squares estimators for the standardized data are related to the variances and covariances of the least squares estimators from the original model using the original data. Now, the proof of this corollary is very straightforward. We're just applying the previous theorem, so theorem 3.9.4, and the result of this corollary follows directly by using the fact that standardization transformations are linear, where a sub x is equal to 1 over the standard deviation of the x's, b sub x is equal to the negative of x bar over the standard deviation of the x's, a sub y is equal to 1 over the standard deviation of the y values, and b sub y is equal to negative y bar over s sub y, the standard deviation of the y values. So it's a straightforward application of the more general result involving linear transformations to get this particular result. So this is a good place to stop this lecture video. The next topic we're going to look at is applying the same kind of thing, looking at the impact on parameter estimates of linearly transforming variables in the case of multiple regression. And in particular, we're going to be focusing on multiple regression where we have 2 explanatory variables or regressors. And so we'll pick that up in the next lecture video.